Hello, my name is Hunter,
Hi, my name is Manfredo.
Hi, I'm Pierre-Alain.
and this is our presentation about the atomic and crystalline properties of our metals and semiconductors.
So, for this portion, we're going to be talking about the crystal structures of our various metals and semiconductors. Our metals are as follows: iron, nickel, and for our semiconductors, we have indium and phosphate. Crystal structures vary, and they can be either a simple cubic, bicentric cubic, a face-centered cubic, or hexagonal close-packed cubic system. In our case, for iron, we simply have a body-centered cubic with atom in the middle, four of them on outer edges. For nickel, we have a face-centered cubic. So we have four atoms on the outside, half them, and then we have no atoms in the middle, but we have them on the sides, and so we have like half an atom here and like quarter atoms on each side, respectively. This also apply. Moving on, we have indium, which is also bicentric cubic, pretty straightforward. And finally, we have phosphate, which is face-centric again. All right, so now we're going to be talking about coordination numbers, atomic packing factors, and theoretical density. For coordination number, it's a bit straightforward. For iron, because it is a bicentric crystal structure, we take a point, in this case, the center point, and we count the atoms all around, like closest and nearby to it. So in this case, it would be 4 on top and 4 on bottom. So our coordination number would be 8. For nickel, it would be a similar process. In our case, we would pick, say, the center one right here, or this side one right here. And so we would count the atoms over here, and then we would mirror it on the opposite side, rather than straight over here, and we would count the atoms on the mirrored side. In this case, it would give us a coordination number of 12. Okay. So now we're going to be talking about theoretical density. Really what theoretical density means is just the mass per unit volume of substance, assuming that it's perfectly packed, and there's no defects, no space, whatnot. So in our case, the formula would be simply the number of atoms multiplied by a given molar mass, all of which divided by the volume of a unit cell, and the multiplication of Avogadro's number. So the theoretical density for iron would simply be 2 multiplied by 55.845 grams per mole, all of which is being divided by 4 over square root of 3 multiplied by 0.126 rates of iron, all raised to the cubic, multiplied by 6.02 times 10 to the 23, which would give us 7.53 grams per centimeter cubic. And similar process for nickel, except in our case, number of atoms would be 4. As first stated, in the atomic packing factor, square root of 2 raised to 0.124, giving us a theoretical density of 9.04 grams per centimeter cubed.
Yeah. So it's time to show the crystalline direction of family of 120. So to do so, it's simple. We have to put first the 120 and alternate the different numbers at first. So at first we're gonna have 120, 1, 2, and 0. And I switch the number, I put the 2 behind, so it give me 102, 102. Now I'll put the 2 in the first place to have 210, and I'll switch the 1. So I'm gonna have 2, 0, and 1. Now I'm gonna put the 0 at first, so to have 0 and 12 and 0, 21. So the principle for the family is to have the 3 numbers and to alternate the position of the different digits. Now we're gonna go on and put the minus, but the minus we don't put the minus right before the digits, we put it on top of the digits. So that's what we're gonna do. So we can have a -1, 2, and 0. We can have a 1, -2, and 0, and we can have -1, -2, and 0. So we're gonna go on to do the rest. For the 102, we have minus 0, 2. We can have 1, 0, and minus 2. And we can have minus 1, 0, and minus 2. We're gonna go with 210. So we can have minus 2, 1, and 0, 2, minus 1, and 0, and minus 2, minus 1, and 0. We can also keep going on with the 201. We can have minus 2, 0, and 1, 2, 0, minus 1, and minus 2, 0, minus 1. We also have 0, minus 1, and 2, 0, 1, and minus 2, and 0, minus 1, minus 2. And for the last line, we have 0, minus 2, 1, 0, 2, minus 1, and 0, minus 2, minus 1. So here the principle is after you alternate the position of the digits, you have to put the numbers on top of the digits and give a minus to every non-zero digit. So that was for the family of 120, and you gotta keep note of the notations. This is what you put at the end of 120. So now we're gonna do the same to show the crystalline direction family, crystalline plane family of 111. So for 111, it's a lot simpler because we don't have 0 and it's the same digits, which is 1. So we don't have to alternate the positions. We just have to put the minus where they need to be. So for 111, we can have minus 1, 1, 1. We can have a 1, minus 1, 1, and the 1, 1, and minus 1 at the end. We can also have the minus 1, and 1, minus 1, 1, and minus 1, and 1, minus 1, minus 1. And lastly, we can just have minus 1, minus 1, minus 1. So again, we just give a minus to every non-zero number. So that's what we do to show the crystalline direction family and the crystalline plane family.
So to calculate planar density for each of these materials, we're going to divide the number of atoms by the area of space that they take up. So to find the area of space that the plane takes up, we're going to relate that to the radius of each of these atoms. So for iron, which is body-centered cubic, that area that we're going to use to calculate it, or the length of one of the sides of the plane, is going to be equal to 4 over root 3 times the atomic radius of iron. So we can plug these values into the equation. The number of atoms in a body-centered cubic plane will be 1, and then this a squared is going to become 4 over root 3 times the radius of iron, which is 0.126 nanometers, all of that squared, and once we solve for that, we get 12.17 nanometers to the negative 2 power. We take a similar approach for nickel, only now we use a face-centered cubic plane. But same approach, number of atoms, which will be 2 now. To solve for A in terms of our atomic radii, we use a new geometry to accommodate the new plane, which is going to be 4 over root 2 times our atomic radii. So we plug in the value of the radius of a nickel atom, which is 0.124, and when we solve it out, we get 16.259 nanometers to the negative 2. Indium, once again, we take the same approach as our body-centered cubic iron up here. We use the new value for the atomic radii, which is 0.157 nanometers, and when we calculate it out, we get 7.607 nanometers to the negative 2nd power. And then once again, for phosphorus, this is a face-centered cubic, so we're going to take the same approach as we did with nickel. We're going to use the same geometry and plug in the new radius, which is 0.18 nanometers. And when we solve it all out, we're going to get 7.716 nanometers to the negative 2 power.
So this was the Team 6, and thanks for watching our presentation of the atomistic and crystalline structures of different metals and semiconductors.